Hello everybody. Welcome to lesson 4. We're going to talk a little bit more about limits, and then we're going to talk about continuity and discontinuity. We're going to be talking about different types of discontinuities, and then we're going to be talking about how to determine continuity. So we'll start with the limits. So obviously we've been talking a lot about limits up until this point. I think I want to make a concept pretty clear here that might have been made clear earlier, but let's make it more clear here. Say that you take a limit of something. Limit as x approaches a particular number c of f of x. If you plug in that number c for f of x and you get a number, then you're done. The limit as x approaches c of f of c is equal to a particular number a, then you're good. You're done, right? If it approaches a particular number a divided by 0, then your options are probably going to be negative infinity, positive infinity, so it's going to diverge to one of those, or it's going to just be opposites, as in it's going to go something like that. It's going to look something like that, right? For example, 1 over x. This is the most famous example. This is obviously going to go nowhere because the right side is going to negative infinity. This should be flipped. Right side's going to positive infinity, left side's going to negative infinity, so let's just make that negative 1x to where if that means left side's going to positive infinity, right side's going to negative infinity, right? And then if you get 0, 0, or infinity, infinity, or like you get a negative somewhere, negative on the bottom, negative on the top, really doesn't matter. So plus or minus, let's just say plus or minus, right? This is where you can make some cool changes, all right? So you can factorize. You can rationalize, which is basically what we've been doing with the multiplying to get that perfect square, as you may recall. Right? Yeah, we have to, we can also apply our trig identities, which is what we did with the sine cosine thing. There are more trig identities, but those are the main ones you're going to use. It's pretty rare that you're going to see something outside of that, but you definitely will see some things outside of that, so we will be touching in on that a little bit. Some more trig identities. So first thing I want to talk about are some important limits that you probably are going to have to know for this. And the main one is the limit as x approaches 0 of sine of x divided by x is equal to 1. This saves an ungodly amount of time. So much time. This saves a crazy amount of time when you're working middle through this problem, right? So limit as x approaches 0 of literally, like, this applies to so many scenarios and it can save you so much time. We'll go over a few examples of those, actually. So let's say the limit as x approaches 0 of sine x, for sine x over x, right? We already know that this is going to be 1, that this entire thing is going to be 1, and we can just take that 4 out, multiply by that 1. Take that 4 out, multiply by that 1, and you can get 4. And the neat thing about this is you can actually do the same thing with anything inside of the parentheses, which you're not normally able to do, right? So let's take pi x, right, over x. We can actually take this pi out. Make it pi times 1, which is pi. That's pretty neat, right? And then we can also use our other other things that we've learned. For example, multiplication or adding. So like sine 3x plus x over x, right? X over x is going to be 1. And then we know that this will be 3. So this is just going to be simple as 3 plus 1, which is 4. Right? Let me get rid of this so you can see this a little better. This will be 3. And that will be 1, because we can split up that denominator, right? And this also applies to multiplying, so let's take sine cubed. Let's do sine squared for starters. Let's do sine squared of 4x squared divided by let's divide that by let's not do 4x squared. Oh, 4x squared is a little weird number. Let's do pi x. Sine squared of pi x divided by let's do 4x squared. Why not? And then what we can do with this is we can actually say that this is equal to the limit as x approaches 0 of sine of pi x divided by 4x times sine of pi x divided by x, right? Because you multiply these two things together, you're going to get 4x squared. You multiply these two things together, you're going to get sine squared of pi x. And that's going to be equal to sine. Now we can take that pi out, and then we can obviously take this 4 out and put it on the bottom, right? So there'll be pi over 4, and then obviously we have a 1 on the bottom, and then we have a pi on the top, because 1 is implicit there. And you can do plus pi over 1, which is just pi. And that's going to be equal to 5 pi over 4. And yeah, so you can use multiplication, division, all these different things in order to find your result. Let's actually go over a problem really quick that I'll create. So the limit as x approaches 0 of sine cubed pi x over 3x x squared. All right. I want you to pause and do this by yourself. I'll go over the answer in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. So this will be sine of pi x over 3x times sine pi x over x times sine pi x over x. And since we have all of these, oh, by the way, I think I did something wrong on that last one. I don't think I multiplied them. I think I added them together. I think I did pi over 4 plus pi when I should have done pi over 4 times pi, which would be pi squared over 4. Right? Okay. So yeah, that's a little mistake that I made there. Okay, so that's that. And then, so that'll be equal to pi over 3 times pi times pi, right? It's going to be pi cubed over 3. And let's see what that is. Pi cubed divided by 3 is going to be like about 10.33, roughly. All right. So that's it for the basic sine limit. We'll go over probably another topic tomorrow. Actually, no, let's go over that topic now. So composite functions are pretty simple. The limit as x approaches a particular number c of f of g of x. You simply have to plug in that number c, and then you have to see if that's going to be equal to f, the limit, as x approaches c of g of x. So basically, you just have to tell wherever that limit's going. So for example, let's say you have this particular function, g of x. Let's say this point is going to be 1, 1. Let's say this point is going to be 1, negative 3. And obviously, remember that we are not going to use the point where f of 1 is defined at. It does not have to be continuous. It just has to have a correct limit, meaning that'll be equal to f of 1, right? And let's say f of x is going to just be equal to the standard linear function of, let's just call this 1, 1, right? That means f of 1 will be equal to 1. I did miss the x-intercept a little bit there. Let's just say that that's there, right? Okay. So that's pretty much it for composite functions. I know I explained those pretty fast. I'll go over a few of them with you. We'll go over 1 or 2. So let's say f of x is equal to x plus 7, and then g of x is equal to x squared. Let's try to find the limit as x approaches 4 of f of g of x. Now, you remember what we do here? We have to do this, limit as x approaches. We have to do f of the limit as x approaches 4 of g of x. And since we know that the limit as x approaches 4 of g of x is going to be 16, because you just plug in 4 squared for that, we can assume it's f of 16. And then we know that 16 plus 7 is going to be 23. So that's the answer. And now I'll let you do one on your own. The limit as, limit as x approaches 3 of g of f of x. So we're switching these now. So remember, you do the same thing with f of x that we did with g of x earlier. All right. I'll give you 3 seconds. Pause the screen. Go again. Unpause when you're ready. 3, 2, 1. All right. So we do the same thing now with g limit as x approaches 3 of f of x. I apologize for going so fast. I just have to be quick with this, considering I'm just on a little tight schedule today. So we know that the limit as x approaches 3 of f of x is just going to be f of 3, so it'll be just g of f of 3. G of f of 3, right? It's going to be g of 10. And we know that, so let me just reiterate, f of x is going to be equal to x plus 7, g of x is going to be equal to x squared, and then we know that f of 3 is going to be 10, and then we know that g of 10 will be 100, so that'll be that answer. All right, let's move on to continuity and discontinuity. So we'll first talk about continuity. How can we prove continuity? Well, there are 3 things. The limit as x approaches c from the right of the function must be equal to the limit as x approaches c from the left of the function. And the limit as x approaches c of, so that basically proves that that exists. This proves limit exists, right? And then the limit, and then f of c must exist. And then the limit as x approaches c must be equal to f of c. All right. Let's look at a practice problem, and then I'll let you do one on your own, and I'll obviously solve it. So the let's say f of x is going to be equal to, f of x will be equal to x squared plus 7, right? And then let's say we're trying to find continuity at a point x equals 4, all right? So that means the limit as x approaches 4 from the left of f of x must be equal to the limit as x approaches 4 from the right of f of x. And we obviously know that they will be the same thing, meaning they'll both be, meaning we know that as it approaches from the left, like let's just see the standard quadratic, we know that it will approach the same place from the left as it will from the right, meaning since 23 is going to be equal to 23, check. That means the first condition is met. The limit exists. And now we need to find f of 4, which is going to be 23 by obvious standards. And now that we know both of them are equal, let's say the limit as x approaches 4 of f of x must be equal to f of 4. And then continuity is proven. So since 23 is equal to 23, continuity is proven. All right? I'll give you another problem to do. So let's do 7 over x squared. And then I want you to try to find continuity at x equals 0. All right, I'll give you 3 seconds. Pause the screen. 3, 2, 1. All right. So the limit as x approaches 0 from the right, is that going to be equal to the limit as x approaches 0 from the left? Well, let's check. So as this goes to a really small number from the right, so negative 0.01, right, so that goes to an incredibly small number. That's going to go to infinity, right? And this is also going to go to infinity from the left as well, actually, because this is x squared. So the limit exists? No, the limit does not exist. Let me explain why. It is because an infinity is the same as a does not exist. In this case, whenever you are trying to find continuity, infinity will never be the primary thing. Also, it's infinity because it's 7 divided by a very small number squared. And whenever you divide a constant by a very small number, it'll go to infinity. All right, that's pretty much it for continuity. I'll now explain types of discontinuities, and then we'll be done. So discontinuities. There's 3. I'll use 3 graphs to identify them. The first one we're going to talk about is jump discontinuity. It's the one we've explored the least. So take this, and then that. You see this point here? The limit from the right is not equal to the limit from the left. So limit from the right of f of x is not equal to the limit from the left. We're just going to call this function f of x. Is not equal to the limit from the left of f of x. And that's what causes that issue. Now let's discover infinite discontinuities. Let's say x equals 1. And we'll go up from here. And then we'll go, let's go down from here, right? We'll call this function g of x. Reason this doesn't work is because the limit as x approaches c is infinite. So that means that f of c doesn't exist. And that's what makes it an infinite discontinuity, because it's going to infinity. And then we have the removable discontinuity. We call this a removable because in some scenarios you can remove that discontinuity. It's what we also call a hole. It's basically the one point in a graph where the limit as x approaches c of f of x, well, it can be the one point, is not equal to f of c, which leads to that discontinuity in that particular point. All right, so I gave you examples of all 3. I'm going to draw 3 graphs for you, and then I want you to tell me what type of discontinuity you think they are. We'll explore more about these discontinuities probably later, as they become more important throughout the units. So I'll draw 2 graphs. I'll do the first one with you, and then I want you to do the second one by yourself. All right? Okay. We'll take this, and then we will draw it like that. Let's just extend that graph a little bit. Okay. Okay, I'll give you 3 seconds. 3, 2, 1. This is a jump discontinuity because the limit from the left is not equal to the limit from the right. And you might be thinking, Jay, there's a hole. True, but it is not irremovable. Because the limit does not exist. Limit must exist for it to be for removable discontinuity. And since limit does not exist in this case, removable discontinuity is not possible. It is a jump discontinuity. And then we'll go with this. Give me a second. We'll draw it like this. It's going to be x equals 2. All right, I'll give you 3 seconds again. 3, 2, 1. All right, this is an infinite discontinuity. Reason it is because... by the way, I hoped you paused the video. If you didn't, that's fine. This is an infinite discontinuity. You might be thinking it's a jump discontinuity, but it's not because f of c does not exist. F of c exists here. And it doesn't always have to exist, but since these limits are going to infinity, obviously, you can signify these by the arrows. That means it's obviously going to be an infinite discontinuity. All right. Have a good day. And I'll see you for lesson 5. We're probably going to be covering, definitely we're going to be covering infinite limits. So I covered these a little bit in lesson 2, but we'll be covering limits in lesson 5. And in the near future, we'll be covering IVT, which is the first of the value theorems. All right, have a good day. Bye.